but this is the last topic that we have to cover for this unit. I have it just kind of generically called more theorems. There are 5 theorems that we have to know in AP calculus. And I probably shouldn't say this as a teacher, but I'm going to anyways. This is probably like the most boring topic in AP calculus. Like, it is my least favorite to teach, and I love calculus. Mainly because it's just a bunch of like words and words and words, and then when we do the problems, it's actually a lot of like writing. So it's like not a lot of like calculating, it's like writing sentences and explaining. So we're not gonna like calculate too much with them, we're just like understanding these things called theorems. Do you want to kind of open it up and kind of say like, we learned these mainly because they show up in 2 different ways on the AP exam. The first way they show up, and really the more common way they show up, is like as a multiple choice question. It's usually those questions, I know you've seen them before, especially if you had an AP class, but it would be something like, which of the following must be true? And you have like A, B, C, and D, and to figure out which one has to be true. Or like, which of the following could possibly be false or something, and you have to choose A, B, C, or D. Or they show up also in kind of when I teach it in this unit, they show up in these word problems that we've been doing. It's kind of like an additional question that can ask us. And the main thing that you want to get from today, there is going to be a lot of writing, but you just have to kind of get these theorems down. But we do just want to get down also, like when we explain our answer, these are the one types of things where I say, like, don't worry about being too concise. Like, just get everything you know down and just make sure you're like very clear about what you're talking about. When I was grading the AP exams this past summer, one of the most commonly places where I didn't give student points was for a question dealing with these theorems. And not because they left it blank, like they had a lot of stuff there, it just wasn't worded the way that College Board expects you to word it when you're trying to justify your answers. Which does also kind of make it annoying. So I think you do have to kind of focus on not only knowing it, but knowing it how College Board wants you to know it. So the theorems that we have, you're going to see if you're following along in the notes, is there are 5 of them. I'm going to skip that first chart for a second. And I hope my OneNote stops glitching. There it goes. But things that we are going to be kind of talking about, like I'm going to give you the formal, like super mathy sounding definition of the theorem. And then I am going to kind of translate it and say like, hey, this is what it means in everyday words. And of course, those of you in class, like you're going to see me actually copying down the formal ones from a sheet of paper, because I just want to make sure I word it again, just like College Board is going to word it on the exam. Just make sure I kind of keep those wordings consistent. So the first 2 theorems that we have, and I kind of group these together in my head, we have the intermediate value theorem and then the extreme value theorem. And then we'll do the next 3 on the next slide. You can abbreviate them, so like the intermediate value theorem, I will just abbreviate IVT. If you put IVT on the AP exam, it's going to be okay. And then the extreme value theorem is just the EVT. And one thing that is nice about the questions, I will say, except for the last 2 theorems we covered, you technically don't need to know them by name. You just have to know like what are their causes and what are their effects. Like you will never see the phrase intermediate value theorem on the AP exam. You won't see extreme value theorem, but you will see the conclusions of those theorems on the exam and things like that. So the intermediate value theorem, and again, this very mathematical definition states if f is continuous and k is between f of a and f of b, there is some k such that f, getting ahead of myself already, there is some c, try that again, in a to b, such that f of c is equal to k. So I told you, it's going to be like, there's a lot of like word jumble. Let's make sense of kind of what this says, and let's convert it into like how we actually speak and not kind of this math theorem notation. All of these theorems are going to have requirements that we cannot use them unless certain requirements are met. The requirement that we need for the intermediate value theorem is you just need a continuous function. If your function is continuous, then you can apply the intermediate value theorem. And basically what the intermediate value theorem states, if I were to take that math definition and put it informally, it basically states that like if f is continuous, then every y value between a start and an ending value exists. I do think a lot of these theorems, like once you kind of see what they mean, you like look at it and you're like, well, duh, why do we need a theorem that means this? What this is basically saying, so like if f is continuous, then every y value between a starting and ending y value has to exist. So like in my graph, we have a starting y value, I have an ending y value. What this function tells us is that we know a starting value and we know an ending value, then every single y value between those two has to exist. Now, it could go outside that region, but we know that at least every single value between those two has to exist. The easiest way that I can explain this, I think, makes a little bit more sense to other students. We just kind of step away from like the function and the math. I kind of think about ages. At some time in your life, you were 2 years old. Maybe right now, you are 16 years old. Well, you can't just like skip over an age. So sometime in your life, you would have been 6 years old. So you don't skip over values when you're counting your age. So same thing with a function. If you know like a low value and you know a high value, all the values in between has to exist. How is this useful? Maybe you're looking at a table of values and you see that you start off with like some negative y values and then it jumps up to some positive y values. You can then conclude, I don't know where, but somewhere the graph has to cross the x-axis. I know that 0 is going to show up between the negatives and the positives. And that's really how this kind of shows up, and that's why it shows up more often like a multiple choice type setting. But basically, if you were to kind of summarize the IVT from a starting point to an ending point, all the y values in between have to exist. Why do they have to exist? Because a function does have to be continuous. And then we have the extreme value theorem, which is going to be similar. I think by its name, you can kind of assume it's going to be talking about extreme value. And it basically states, if f is continuous, then f has an absolute minimum and maximum on the interval, and put brackets, not parentheses, a to b. So that is what the theorem says in its formal kind of math definition. What does this basically mean? A function will have both an absolute min and max on a closed interval. And when I say a closed interval, that means our endpoints are having brackets and not parentheses. So basically your endpoints are going to be included in the graph. Again, a lot of these theorems, you don't have to know it by name. That's why I kind of think you think about it hard enough, like it makes sense. If you have a graph and you know that both the endpoints are in a bracket, meaning that they're included, then you know without a doubt that somewhere along that graph, there has to be an absolute maximum. You may not know where it is, but you have to know that it does exist somewhere. And then somewhere along that interval, there has to be an absolute minimum. And that does kind of go back to, if you remember when we first talked about doing a Candace test, sometimes we tossed out and said, hey, there is no absolute max or there is no absolute min because it ended on parentheses. Well, there never is going to be a time where you toss out an answer if you always have brackets. So it does kind of make sense. If you have a closed interval, even if you don't know what the function looks like, you know without a shadow of a doubt that there is going to be an absolute min and an absolute maximum on that interval. Now we haven't done any examples of these yet, but are there any questions just on like the wording of those two? And I should also highlight what's required. So in the intermediate value theorem, it had to be a continuous function. To talk about the EVT, you have to have a continuous function, and you have to know the endpoints has brackets on it and not. And when I say like it has to have it, so like if you said the function was not continuous, then you couldn't make these conclusions and these justifications. So that's why we're kind of emphasizing what's going to be required of them. I'm going to come back in and fill in that top part once we do all of the theorems. Next slide, we have the remaining three theorems that we have. I have Rolle's theorem, and then we have the mean value theorem for derivatives, and then the mean value theorem for integrals. Rolle's theorem is the only one that really has like a name that doesn't sound so formal. Not really an abbreviation for it. You can just call it like Rolle's, and we'll know what we're talking about. But again, you don't have to know the name of these theorems on the exam. You just have to know like the requirements and then what you conclude from them. Rolle's theorem, it states if f is continuous or differentiable, and f of a is equal to f of b, there is some c in the interval from a to b such that f prime of c is equal to 0.
This procedure, f is.
If, oh yeah, I said if. I said f, then it read it, yeah. If f is, thank you. So let's think about what this means. Like, I think sometimes when you see like the math, it has like a lot of like math jargon. Let's kind of interpret it into more of like everyday language. I'm going to highlight the requirements. So for the Rolle's theorem, the function has to be continuous and differentiable. I don't know why we're or there. It's like the third time I wrote it. You think I would get it today? And differentiable. And the other requirement is you have this thing where it says f of a is equal to f of b. So that one does have 3 requirements. The function has to be continuous, differentiable, and you have to have this statement f of a is equal to f of b. We know what continuous is. Maybe we need to review what it means to be differentiable. When I say a function is differentiable, what am I meaning by that? You can take a derivative everywhere. So basically every single point has a derivative. And when I say you can take the derivative everywhere, so it has like no jumps, no holes, no vertical tangents, no corners, no bezels. So we can take the derivative everywhere. And then we have this statement that f of a is equal to f of b. What would it mean if I say f of a is equal to f of b? Same y values. You can kind of see in the graph, we have the same y values. And then we also see, so if you have the same y values, it tells you that basically between those 2 y values, there is some c between a and b. You have this statement that f prime of c is equal to 0. What would it mean on the graph f prime of if f prime is equal to 0? The slope is 0, we have a horizontal tangent line there. So basically, I think this one does kind of make sense to put it in everyday words. If f is continuous and differentiable, so again, those requirements have to be made, and 2 y values are the same, there is at least one horizontal tangent on the graph. And again, I think that kind of makes sense when you think about what a graph has to look like. So if a graph is continuous and differentiable, there's no like jumps in it, there's no holes in it, there's no sharp turns in it. If two y values are the same, the only way to get from one y value to that same y value is that graph is going to have to turn around somewhere. When that graph turns around, what is it going to create? It's going to create a horizontal tangent. We can kind of see in this one, the graph went up first and then down. When it turned around, we can see that, yes, there was a horizontal tangent. Say you didn't know what the graph looked like. Say you just knew like, hey, here's one y value. A little bit later, you had the same y value. You may not know what the graph looks like, but I know for certain that somewhere between those 2 points, there has to be a horizontal tangent somewhere. There could be more than one, but I know the only way to get from one y value to the same y value is that the graph will eventually have to turn around to get back to kind of where it started. So this is one that would have like 2 horizontal tangents, but we know because of Rolle's theorem, there has to be just one of them. Questions on Rolle's theorem? And again, we will do examples of these. I just kind of want to get the theorems out of the way first. And then the last 2 ones we have, they both have the same name. So I did want to kind of talk about the naming of them. We have the mean value theorem for derivatives, and then we also have the mean value theorem for integrals. Notice that for that first one, I wrote the mean value theorem and I put the derivatives for brackets. And that's because if you just say the mean value theorem, it's implied that's going to be for derivatives. So this is the one that you do need to know the name for, or really the 2 that you do need to know the names of them. And when the AP exam uses this one, they'll just say the mean value theorem. They won't say the for derivatives part. You just have to assume they're talking about the for derivatives. So when I'm abbreviating this one, I will just kind of refer to it as the MVT. That's kind of like the main one that we have. There is another mean value theorem, but it's the mean value theorem for integrals. When they're talking about that one, they will always have to say for integrals to distinguish it from the one that's for derivatives. Why couldn't we just come up with a different name for it? I don't know, but that's just what their names are. We have the MVT, and then we have the MVT for integrals. These are also the only 2 where we end up solving for something. So all the other ones, the intermediate value theorem, the extreme value theorem, and Rolle's theorem are all kind of used to like justify things or determine the existence of something. For both of these, we often will be setting up an equation and it will have something like solve for C or like find the C value that makes this statement true. And it will be the same thing for the integrals. So the equation that we need to know, of course, we do want to go ahead and get the requirements out of the way. The mean value theorem for derivative is basically going to be if f is continuous and differentiable, there is some c in the interval from a to b, so that, and then there is an equation that goes along with this one. And the equation that we have for the mean value theorem for derivatives, it states that at some point, the derivative at a point is equal to the average rate of change over the interval. And again, how these problems are often set up is they'll say like, hey, find the value of C that satisfies like the mean value theorem for derivatives or something like that. To put it in kind of everyday words, again, if f is continuous and differentiable, there is x equals c, and then it's going to satisfy that equation. That is the equation that you want to know. To kind of put this equation in words, I think there's kind of 2 different ways you can think about it. We see the derivative of c. Well, the derivative is the slope of what type of line? The derivative is the slope of which one? The tangent. The average rate of change is the slope of the secant. So basically, this equation says somewhere the slope of the tangent is going to be equal to the slope of the secant. That's one way to think about it. It helps you kind of memorize the formula. The other way, so yes, that is the average rate of change that we discussed earlier this week. And the mean value theorem for derivatives states that at some point the average rate of change is going to be equal to the derivative, which is also called the instantaneous rate of change. I think this one is also pretty easy to see kind of visually on the graph. So again, if you're looking at that graph I have on the right-hand side, that function is continuous and differentiable on that interval. You could find the slope of the secant line. I don't have numbers on here, but we know how to find the slope of a secant. And I think you can even eyeball it along that curve. You can kind of eyeball and see there is a point that has a tangent that has the same slope as that secant. I'm just going to kind of eyeball it myself. It looks like it's about right there. And so this tangent line has the same slope as the secant line. And ultimately, you would sometimes try to find the C value of where that is occurring at. So that's the mean value theorem for derivatives. It uses the average rate of change. So then we also have the mean value theorem for integrals. What formula do you think it's going to use? The ones in front, the average values. We have the average rate of change that shows up for the derivative, and we have the average value that shows up for the mean value theorem for integrals. So we have if f is continuous, doesn't require it to be differentiable, but there is some c in the interval from a to b, so that, and then we have our equation. The equation we're using for the mean value theorem for integrals is going to be the function itself, so f of c, not the derivative, is equal to the average value of the function. Putting that kind of in everyday terms, if f is continuous, then we have basically the y value at some point is equal to the average value of the function. I think this one's a little bit harder to visualize. Like in that mean value theorem for derivatives, it's pretty easy to see that yes, at some point the secant line and the tangent line would have the exact same slope. The average value kind of formula, however, that it literally means you're finding the average of all the y coordinates. And basically what it states is, hey, since this function is continuous, if we were to find the average of all the y values we see on that graph, then, so again, I'm averaging all those y values together, there is going to be some y value that's exactly equal to the average that you have. Easiest way you can kind of explain this is we kind of step away from functions. Let's think about the simplest gradebook we can. Say you have a class and it only has 2 grades in it, and you make a 90 and a 100 of those 2 grades. What would be your average? 95. That doesn't mean you made a 95 on an assignment. It was just the average of 2 assignments. Functions are unique. Like, it's not like you make a 90 and a 100. A function says you can basically make everything starting at 90 all the way up to 100 inclusive. So like all the decimals, everything in between it. So at some point on the function will literally be equal to its own average. It doesn't really happen when we have kind of discrete values. Again, the big idea with both of those, though, is not really the interpreting of it. They often will have you just solve for the c that makes the equation true. So you do want to kind of get in your head, that's the mean value theorem for derivatives, and then this is the mean value theorem for integrals. And they do have some different requirements. So the one for derivatives does require it to also be differentiable. The one for integrals just requires it to be continuous, since you're not taking a derivative anywhere. Yes, Armando?
If you were talking about the mean value here for integrals, and you had to give units, would your function be a rate, so that would be in
You normally are solving these for like the units. It's more of like when we're talking about these theorems, we're mainly on like the theoretical side of math. So we want to be, these last two typically aren't going to show up on a word problem. The other ones could, but not these last two. Any other questions kind of about this wording before we kind of look at a few examples? All right, so just stay with me a little bit longer. I don't plan on teaching to the bell. Like I know there's a lot of words, so I just plan on doing like one example in 2 parts, and then we'll stop notes for today and then finish it up tomorrow. Because again, it is a lot of writing. I think it just takes a while to kind of sink in. They want to go kind of back to this little chart just to remind you that like to use these theorems, we do have to have certain requirements. Some of them just require the function to be continuous, and some of them require it to be both continuous and differentiable. The ones that require it to be continuous, and again, we already wrote this down, but to kind of summarize it, was the IVT, the EVT, and the mean value theorem for integrals. And then we have 2 that requires it to be continuous. They're the ones that both talk about the derivative, and that is Rolle's theorem, and then also the mean value theorem. For derivatives, we don't have to say, if we just say MVT, that's going to imply it's for derivatives. So what I find students sometimes have trouble with these topics is it really is kind of you're using these theorems to justify some answer. So you have to, when you're justifying the theorem in math, you have to state clearly everything that the function satisfies before you can use the theorem. So for example, we're going to look at the first example that's going to use the intermediate value theorem. Before I can start justifying with the intermediate value theorem, I have to make sure I clearly state that it has satisfied the conditions required. Meaning I have to state clearly that, hey, this function is continuous, and that's why I can explain my answer this way. More and more recently on the AP exam, I have been seeing that when they give you kind of like their given information, they just tell you that their function is differentiable, and they don't mention that it's also continuous. And so I often find students are like, well, it says it's differentiable, but I need for it to be continuous. And you can, if a function is differentiable, then it also is continuous. Like it can't be not continuous and also differentiable. And so I have this statement on here, like that seems like a really kind of just short statement. That small statement, if it doesn't tell you your function is continuous, but it does tell you it's differentiable, you kind of see what I mean by that. That little sentence, those 3 words can save you like 1 to 2 points in a first response question. Like it seems small, but again, you want to make sure you're clear with these problems about mentioning everything you possibly can. So let's look at the first example. I copied over a question from the AP exam for the first part of it. I took off like the solving part, and I just left the part dealing with the theorem. I did also realize, if you are following along in OneNote, that second question, I realized I typed it in wrong when I was trying to make up the question, and I typed in velocity, and it definitely should say acceleration. And we don't really need that whole word problem if you're trying to avoid writing all that down. Technically, all you need to write down, if you are taking notes in your own sheet of paper, is this statement right here and the table. The rest of it's just kind of like extra stuff. And so how these questions work is, again, we're using these theorems to justify why we know something is true. So I have this table here. This is a table of the acceleration function. And I only know the acceleration function at the time of 0, 2, 6, and 8. It does tell me that the acceleration function is continuous and differentiable. That's a big clue that we're probably going to have to use a theorem to kind of justify our answer. And so let's look at that first question that we see. We're just going to do these 2 questions today, and that's where we're going to kind of stop, and then we'll pick up tomorrow. And so this first question says, does there have to be a time t, where t is between 0 and 8, when the graph of the particle's acceleration is equal to 3? And then we want to be able to justify our answer kind of using these theorems. Again, when we use these theorems, we don't have to justify it by name. We just have to make sure we're very thorough and clear and explain it completely. So looking at this table, I see the acceleration starts at -2, and then it goes to 1, and then it goes to 5, and then it goes back to 1. If that is a continuous function, would the acceleration ever have to be 3? Yes, and in fact, how many times, and it asks about how many times do we know it at least has to be 3? Twice. Could it be equal to 3 more than twice technically? Yes, because we don't know what's happening exactly between 0 and 2. It could be going up and down like crazy. We just know those two values exactly. But we do know that it has to be equal to 3 somewhere. That's why I sometimes say, like, these theorems really are common sense if we look at it. Like, if you go from 1 to 5, clearly you crossed over 3. The hard part is just making sure you explain your answer thoroughly to make College Board happy. So our answer is going to be yes. So of course, I'll start that way. Let's make sure our answer is clear. Yes. And then we want to go ahead and form our answer. So again, we don't have to form it by name. If we did want to name it, what theorem are we using to prove that it had to cross 3 at some point? The intermediate value. The IVT is the one that's going to help you find those two values. I'm not going to name it because it's not required. So I'm going to say since A is continuous, and then I'm going to kind of pause there. So again, you always have to state the reason why you can use a theorem, even though you're not naming it by name. The only reason that we know it crosses 3 is because this is a continuous function. So you have to state that somewhere. And then we just basically want to say, like, choose a value that's lower than 3 and choose a value that's higher than 3 to show that it would be crossing it eventually. And how do I do that? I'm going to say something like A of, and I could choose 0 or 2. I'll choose 0. A of 0 is equal to -2, and that is less than, not 0, but that is less than 3. What's the point of saying that statement? We're basically saying, hey, we're starting at a value that is lower than 3. And then what happens after that, and A of 6, I want to find one that's bigger than the one we're looking for. A of 6 is equal to 5, which is greater than 3. What's the point of saying that statement? We basically said, hey, we have this point where it's lower than 3, this point where it's higher than 3. Since it's continuous, there is some C so that A of C is equal to 3. And that would be a justification that would receive full points on the AP exam. And it's usually 2 points out of 9 on a 3-response question. So like, take the time to kind of explain it thoroughly. There are some things you could add to make it like a better explanation, but at a minimum, that is what you would have to say. Things you could say extra, not going to get you more points, but just make your answer a little bit stronger. You could squeeze in like the theorem's name, so like by the intermediate value theorem, blah, 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 blah. I would be careful though, like if you're going to name the theorem, be confident that that's a theorem that you're using. So if you put by the MVT, but you just use the IVT, you just made a correct answer or a wrong answer. So you don't have to name it by name. So sometimes it is better just to leave it off. And then the other thing you can kind of make a little bit more clear, again, it wouldn't be required, but it was asking me to justify something between 0 and 8. And the values I used was from 0 to 6. It's kind of logical. If something is true from 0 to 6, would it also have to be true from 0 to 8? Yes. Again, this is just extra, but you could say something like, and the interval from 0 to 6 is within 0 to 8. Again, what I have in black there would be extra. The minimum you would need is, of course, just that blue. You mentioned what allowed you to use the theorem. You mentioned that you had a point below and then a point above what you were looking for. And then you kind of answer the question. Yes, there has to be some point where the acceleration is equal to 3. Questions on that? Yes, Evan.
So when we're like doing all this diagram stuff, can we abbreviate so that or such that?
With the symbols, you can, yes. All right, so let's look at the second one. Again, please change it if you're following along in OneNote, since we definitely have a table of the acceleration, and that's what I definitely want to talk about right now. It says, does there have to be a time t, again, within that same interval? when the graph of the particle's acceleration has a horizontal tangent line, and then justify your answer. Looking at this table, how do we know that this graph has to have a horizontal tangent line somewhere? We have two ones, and then technically what other reasons allow us to know there's a horizontal tangent? It's both continuous and differentiable. What theorem are we technically using? Rolle's theorem, but we don't have to name it by name, but we are using Rolle's theorem, kind of the idea behind it. So again, my answer would be, again, yes for this one. So we have yes, since the acceleration is continuous and differentiable. And then how did we know it was because we had those two y values that were the same. So I just want to make sure I'm clear about what those y values were. That was at 2 and 6. So since A is continuous and differentiable, and A of 2 and A of 6 are the same y value, there is some C in the interval. Let me not be complex. There's some C such that A of C, A prime of C, is equal to 0. A of 8. Say again.
So A of 6.
Oh, it's A of 8. A of 8, yeah, I get what you're saying. I'm like, what are you talking about? Yes. 8. That's at a minimum what you have to say. Again, I think that kind of makes sense logically. Like, hey, it's continuous, it's differentiable, we have the same y values, so at some point, this graph had to turn around, and when it turned around, it made a horizontal tangent line. We just had to kind of find like a formal way to state it. Again, if you just want to be extra, you could add in what theorem you're using. So it would be by Rolle's theorem. And then you could say something like, since we're talking about from 2 to 8, you can say something like the interval 2 to 8 is within, or basically a subset of the interval from 0 to 8. But again, that's what I have in black would not be necessary for you to use. Questions on that? All right, so we'll finish these notes tomorrow, because again, I do want to just give you time to like process this, because it is a lot of words, more than we're probably used to in calculus. Tomorrow we'll just do a warm-up with like another one with the table and kind of justifying our answer. We'll look at an extreme value one, and then we'll look at the mean value theorem ones. Again, those are going to be the only ones where you actually have to solve an equation. The homework that goes along with this one, I feel like I adjust it every year just to kind of figure out how I want it. It looks long, but it actually should go by pretty quickly. I only want you to do the highlighted questions. There's a whole bunch of questions on there. Just do the ones that are highlighted. The front page is basically like a true false. I don't need you to do any on the second page. And skip this page for now because we haven't done any of the equations. And then I ended it because again, a lot of these questions are like multiple choice type questions. And it's literally like something like this, like which of the following would possibly be false, or like which of the following must be true. So a lot of these are just making sure you understand just the conclusions of these theorems instead of actually having to solve anything to find the value. So we'll finish these up tomorrow. Definitely let me know and kind of reach out if you still have questions or anything like that.